All right, hello everybody here. So this is the first of our quadratic, like n squared times sorting algorithms, and this is called selection sort here. So you might remember that we have basically two sort of strategies for doing n squared sorting. We can pick a position and say what goes here, right? So like what goes in position 0, what goes in position 1. We call that a what goes here style sort here. And the other strategy is we can pick an object, like a value, and say, where do you go? Like, okay, here's the number 12. Where should that go in the sorted sequence? And we call that a where do you go style sort here. So selection sort is a what goes here style sort. So we're going to loop through the positions through 0, n minus 1, and then for each position we're going to say, what goes here? What goes in position 0? What goes in position 1? What goes in position 2, and so forth there like that. So like a skeleton of selection sort looks something like this, right? We've got our vector, selection sort. All of the n squared ones are in place sorts. So that means we're taking our vector as a reference because we're going to modify the stuff in the vector directly there. So we're just looping through the positions in our sequence, and then for each particular I, we want to find the element in the sequence that goes in position I and put it there somehow or another. So if we run the loop in this order, in the order 0, 1, 2, 3, like that, right, that basically boils down to, okay, we need to find the smallest element, and then the second smallest element, and then the third smallest element, and so forth there like that. So like, let's say that we're trying to figure out like what goes here. What goes at position 0 there like that. So what we're going to do is we're going to do a loop over the entire thing to find the smallest thing, right? Like that's what should go at position 0 is the smallest thing in the entire array. So or the entire vector, excuse me. So we just loop over the whole thing, and we want to find the smallest element between I and the end there. So like, let's say we find it here, right? So we want to put that thing into index 0. We could insert it and like shift things around here, but the easiest way to sort of put it there is to just swap, right? So swap the thing at position 0 with the smallest thing that we found there. And that kind of locks in position 0. Like the smallest thing is there, so I know that nothing is ever going to go before that, right? I don't need to sort of modify that there. So now I'm looking for what goes in position 1, and the answer is the second smallest thing. Now, normally, finding the second smallest thing in an unsorted sequence is a little bit tricky, right? You need like two variables. You have to sort of rule out the smallest thing here. But here, it's easy because I know where the smallest thing is. So if I just start my search and I do like literally the same search for the smallest thing, but I tell it to only search this part of the vector, what it finds will be the second smallest thing here. So I don't have to like, do something different to find the second smallest thing. I just tell it to search the part of the vector that does not include the smallest thing. The smallest thing is there at in the sort of index 0 there like that. So let's say we find the smallest thing over there. What are we going to do? We're going to swap it to position 1. Now we've locked in the first two things. So if we just sort of keep going, right, eventually we will lock in all the things here like that. And then when we have one thing left, that thing is guaranteed to be the biggest possible thing. So I don't need to like swap it with itself. That would be silly. I mean, you could, it wouldn't hurt anything, right? But like I can stop when we hit n minus 1 there like that. When I is n minus 1, there's only one thing left, right? So we're like, hey, what's the smallest of just one thing? Well, that's got to be the thing itself. So at that point, we're sort of done there like that. So normally finding the case smallest element of a sequence is not like trivial, but for us it's easy because we've already got the sort of smaller elements tucked away off to the side here, so we don't need to worry about them there like that. So like, let's notice like the shape of this, right? So we're gonna have an outer loop, which is I, keeping track of like what position am I interested in here like that. And then inside that, I have an inner loop, J, right, that is doing the search for the sort of smallest thing there like that. So this is the implementation of selection sort here. So we take our vector by reference because it is an in-place sort. We're going to iterate over all the positions and say what goes in 0, what goes in 1, what goes in 2. We need to find the index of the smallest thing. We don't just need the value of the smallest thing. We need to know where it is because we're going to do a swap targeting it here. So smallest is the index of the smallest thing that I've seen so far here. Then we do a loop starting at position I plus 1, because we've already kind of looked at I by storing that into smallest there like that. And then we just scan forward and we say, okay, if the jth element is smaller than the current smallest thing I've seen, then we update smallest to j. And then once we're done with that loop, smallest is the index of the smallest thing. So we're going to swap that with the thing at index I there. And then let the outer loop, the I loop, continue. We've seen this loop pattern before, right? Like this is the sort of pattern of where it's like, okay, the first loop does n minus 1, and then the next one does n minus 2, and the next one does n minus 3, all the way down to 1, and then 0 there like that. So the total work that we're doing here is this sum here. So if you do this sort of sum doubling trick, you end up with n times n minus 1 over 2, which of course inside of a big O is O of n squared there like that, right? Now, if we sort of step back one slide here, let me pop back here, right? There's no break or return in either of these loops here. So both of the loops always run all the way to the end. So that means O of n squared is both the worst and best case runtime there. Selection sort is not adaptive. It doesn't like run faster in big O terms if you give it stuff that is like already partially sorted. You can literally give it a vector that is like already sorted and it will still kind of like go through the motions and like swap each thing with itself there like that. Another useful thing to do is to do a little bit of a stepwise analysis on selection sort. And we're going to count the number of comparisons we do, right? How many times do we compare elements of the sequence? So I'm not counting like the loop comparisons. I'm just counting that sort of bit right there. And then counting the number of swaps. So the comparisons happen inside of the j loop. And we've determined that that loop runs n times n minus 1 over 2 iterations. So the number of comparisons is n minus 1 over 2. But the swap only occurs in the I loop there, which runs n times. So what we have is we do basically n squared minus n over 2 comparisons. But for swap, we do only n swaps there like that. And this thing here is kind of interesting. Like the other algorithms we're going to look at do more swaps. They do potentially n squared swaps in the worst case like that right here. So the nice thing about selection sort is it only swaps each thing once. It doesn't never sort of like swaps a thing more than one times there like that. So that's kind of a nice thing to know. If like swaps are expensive, then selection sort is sort of conservative in that regard. There's a few sort of variations on selection sort, right? So for example, we could do a selection sort on a singly linked list, because we only ever go forward, right? We'd only move in the forward direction here. So switching from an array to a singly linked list doesn't change anything about the sort of analysis here. So if we have a pointer to the head of a list here like that, I starts at the head, I is not equal to null pointer, I equals I arrow next, like that, right? The smallest is now a node pointer, and then we just do our j loop in terms of node pointers instead of in terms of indexes here. So nothing about the analysis changes if we switch from arrays and indexes to linked lists and node pointers, which is kind of nice, right? A faster variation, like faster in real world terms, but not in big O terms, is what's called a double selection sort here. So the idea is we're going to modify the inner loop, the j loop, right, so that it finds both the smallest and largest values at the same time there. So we're sort of saying, okay, of the stuff that I have left to search, what's the smallest and the biggest thing here? And then we swap the smallest thing to the beginning and the largest thing to the end. So we're sort of filling in the sort of sorted sequence from both directions there like that. So if the standard selection sort is like approximately n squared over 2, this one is kind of like n squared over 4. Like basically, if you want to sort of picture, right, the normal selection sort looks like this, right? Here, like this part is the work that we're doing. So this is like n by n. This version here, the double selection sort, let's see if I can draw it like that, right? Looks like this, right? It's filling in the sort of this upper quadrant triangle of an n by n squared there like that. So again, like, n squared over 4, n squared over 2, in big O terms, those are the same. But in real world terms, you will notice that a double selection sort finishes like slightly more than, like less than twice as fast as the plain selection sort there. So anyway, here's a summary on selection sort. Runs in n squared time in the worst case, like that. So it's one of these sort of quadratic ones here. It's not adaptive, which means it runs in n squared time in the best case as well. Like it always runs in n squared time there like that, right? It's in place. The only memory we use are the sort of loop variables, the variable smallest, and then like, there's a little bit of memory being used inside the swap function, but it's a constant amount of memory. We're not making a copy of the sequence to sort it. It is not stable though. So if you remember stable, right? Stable means you can use a sort as part of sort by first name, then by last name, then by social security number, then by salary, and it will sort of like make sense. So here, the long distance swaps that we do kind of move things further than a stable sort wants them to sort of move there. So it is not stable. If you switch the swap for an insert, then it becomes stable, but it becomes slower because an insert involves like another sort of nested loop in there like that. So anyway, selection sort's generally slower than the other n squared algorithms, but the number of swaps sort of like being predictable, like sometimes that's an advantage. Sometimes you want to sort of say like, okay, I'm only going to swap exactly n times there like that. So that is selection sort there. If you want, you can move on to the next one here, which is going to be bubble sort.